drag, which is bad because you don't want very much drag, so you have to control how much downforce you want and really how much you need, which is going to be dependent on each car, the track. So we tried to get a good estimation of that. Of course, aesthetics is considered in the design. You don't want some gigantic wing that's hideous and unnecessary, and high-speed reliability. So we couldn't have a bunch of little things that would be breaking off because the car goes 140 miles an hour. So it has to be pretty durable and on there very well. So this is the model. It's a 3D scan of a 1995 BMW 3 Series. It's a very common car and used a lot in racing, so that's what we're using.
Yeah, and one thing to note is that because of the file nature, we had to shrink wrap the body, so it looks a little bit smoother. So that's maybe one limitation of the the realities of CFD, is you have to make some assumptions and smooth things out a little bit. So the first important part of doing CFD and making sure you can get accurate results is creating the fluid domain to be used for your simulations. And for a car aerodynamic simulation, you can see this image on the right here. It's recommended to use many multiples of the length of your vehicle in order to capture all of the significant points and to capture different wake fields that come from the wind passing over the car. So this is one important aspect, is you create the body around the car to be the enclosure, and then you subtract the body of the car to act as almost a wall to simulate the wind flying over it and it being a solid body that it can't go through, obviously. So this is a static simulation. It's not a dynamic mesh, for example, like you would do a wind turbine to show rotation. This is just a static body that is subtracted from the fluid domain. And CFD is governed by the Navier-Stokes equations. That's kind of the fundamental idea. You create a mesh to solve for the values that you're looking for, and at every node and element you solve for these 5 Navier-Stokes equations. So that's part of the difficulty with CFD, is that it becomes computationally expensive. It takes a long time to run some of these simulations, and so it can get quite costly in that regard. And the limitation with this project is that we were running it on a laptop, so it couldn't get super accurate results. And also, the student software has a limitation on how many nodes and elements you can use. So that was one limitation. The next step after creating the fluid domain for CFD is to generate a mesh. And to get accurate results, you want as fine mesh as possible. But the issue with that, like I was saying, is the computational expense. And so the idea is you want to enhance the mesh around the important pieces of your model. And so for that included doing a body sizing around the car, so the nodes are super small, so you can calculate those Navier-Stokes equations and get super accurate values around the car. And so what that looks like is this. This is a cross-section of the fluid domain, and as you can see, there are large elements on the left side. On the right side is the inlet, on the left side is the outlet. And so you can see around the car, you can't even see all the nodes that are being displayed in this image. So there are 241,000 nodes and almost 1 million elements in this simulation. You could easily go into multiple millions, but we had to keep it limited for this simulation. And here's a close-up of the body. You can see very dense mesh as compared to the other regions that aren't as important. And you can also notice around the car is those 3 layered lines. Those are called inflation layers, and those also enhance the calculations around that body. So the idea is to get a super accurate calculation around the vehicle. And that's displayed here. Those lines allow you to calculate increasing accuracy around those points. And so this is super important for especially car aerodynamics, is to get as accurate values as you can around these important areas. And then boundary conditions. Once you create the fluid domain and then you create a mesh, you then need to go into your CFD solver and basically give it all the assumptions you're making. So in the velocity inlet from the domain, we, as shown here, just as an example, is like a 35 meter per second wind velocity going through the inlet. And then some base assumptions for turbulent intensity and turbulent viscosity ratio, which are standard. We just use recommended values. And then for the outlet, the key parameter here is the zero gauge pressure. That is the most important part for the outlet. And also the same here is the same assumptions for the turbulent values. And then for the walls surrounding the domain, not the bottom wall, which we'll call the road, this is given as a stationary wall with the no-slip boundary condition and a roughness constant of 0.5, which was again a base value that the software recommended for this application. And then the road, which is maybe the biggest deviance from what we saw previously, but in this condition, we gave it a moving wall condition with the same velocity as the wind inlet to represent the moving road condition that you would see with a car. And then probably the most important aspect of this is giving the software some reference values. So like the key takeaway here, and we talked about it in class, is the frontal area of the vehicle. So this is a key portion towards calculating lift coefficients and drag coefficients and their forces. And so in these reference values computed from the inlet, mainly you see the frontal area and the length of the actual vehicle, along with other assumptions about temperature and viscosity. And so once you have identified all of that, then came to residual values, which more or less shows how long it takes for the software to reach conclusive values. And so for the first simulation, we ran 1,000 iterations. This took probably over an hour to do. This is more of a simple model, so it can easily get longer than that. But as you can see, after about 200 iterations, it basically reached the values we want to see, and it converged to decently acceptable values, considering we have to make 10, 20 more simulations. So from here on out, we stuck with 200 iterations. And then here are the results. As you can see, for the base model, we have the coefficient of drag came out as 0.304, which is very close to the advertised number. And then the coefficient of lift came out as negative 0.15, which represents downforce. But obviously for the race car, we want to enhance that, so that will come. And then the drag force, about 389 newtons, and the lift force about negative 192 newtons. So looking more at the results, this is a nice image showing static pressure, more or less showing concepts we learned about stagnation pressure. All of the front-facing areas are all super high pressure, and then as the air comes around different areas, like behind the mirror, for example, is low pressure. It's a blue zone. So this is a good representation of that. And same here, you can see the velocity moving along the car. The velocity is 0 because of the stagnation point at the front of the car, and the velocity increases as the area changes. So at those points, the velocity increases, those like dark red points, and then it flows over the car, and a very low velocity zone and gradient at the back of the car. And then just some more images showing this. This is kind of the wake of the car being shown here, and the velocity. And kind of to show the importance of a large fluid domain is to show this is like the enhanced length of the velocity turbulence. So it spans quite far. So it's quite important to have a large fluid domain. And then this is a little video showing flow paths. So you can see it's moving over the car, and slow, there's a much lower velocity at stagnation point there. And it's increasing velocity at these points here. And obviously the wind is moving past the car, and then there's a little bit of a turbulence zone there at the back. So showing the same concepts from those other images.
So those were all calculations for the base model. So now we got to designing the modifications to it. So we started with the splitter and lowering the ride height of the car. So we actually brought it closer to the ground and added that splitter. And since neither of us are aerodynamics engineers, we decided to crib it from Chevy Corvette. That's actually a ZR1. So I basically tried to take the design of that splitter and modify it to work with the body of that car. And for the most part, it worked pretty well. There's definitely some improvement that can be made, but I think for what we're doing, it's a good start. And so this is actually how the splitter works. So its design function is to literally split the air between a high pressure zone and a low pressure zone. The high pressure zone's on top of the splitter. And this is kind of a section where we get into some computing limitations, because if you look at that little C channel where all the red buildup is, that's actually a grill of the car. So that air would technically flow through into the engine bay, but since we can't really model that accurately with the software, it's kind of just a design flaw, I would say. But the premise is still there. So you can see it's splitting the high pressure and low pressure air, and you want the low pressure air to go underneath the car because that basically creates a vacuum effect and will suck the car into the ground. And so these are our next design choice, which are their fender strakes. I cribbed it from a Porsche GT3 RS, and again, we've kind of run into another software limitation here, and it's that the turbulent air that would come off of the wheel spinning is what these look to re-streamline and reattach to the body, because the wheels will create a lot of flow separation just because they're kicking up so much turbulent air. And we can't really model this in ANSYS. So we are not able to simulate it at least easily with a wheel spinning to show that flow separation, but if Porsche did it, it must be good, so that's why we did it as well. We did run a simulation with these values, and unsurprisingly, they didn't really change much. The drag slightly increased just because there's slightly more frontal area showing because of the way that the strake bends. Our next design choice was a rear diffuser, which sort of pairs very well with the splitter and lowering the car to the ground. So what this does is it tries to extract all of the low pressure air out from underneath the car so we can welcome in some new air and keep the downforce going. And I cribbed this from a Audi R8 DTM race car, which you can see right there. And its diffusers are pretty much one and the same. They all work on the same fundamental concepts of just streamlining the air out of the car and reintroducing it to the atmosphere as a free jet and diffusing it, if you will. And like I said, so this is how it works. You can see at the front of the car we have low pressure air, and as it works its way to the back, it increases pressure, which is going to increase the flow and get it out from underneath the car. And if you see right at the back of the diffuser, you can see just at the front of it, it creates a high pressure zone because it actually sticks into the path of the airflow and then works on diffusing it all the way back to a equalized pressure at the rear of the car. And then this is another section where you can see it kind of doing the whole free jet thing, which is actually pretty cool. It almost looks like the back of the car has a rocket engine on it. And you can see how it's trying to diffuse back into the atmosphere in the wake turbulence of the vehicle. And naturally, so this actually helped us a lot with our drag coefficient. So it dropped it by about 0.3, or 0.03, excuse me, which is pretty considerable in the terms of drag. It also slightly decreased our lift coefficient, which is all good things. So next was definitely the most eye-catching thing of the car, which is the rear wing, and it is built in to have cover up the rear wheels, so it kind of gets into the fender strake things like we were talking about on the Porsche. And I cribbed this from a hill climb racing car, and these cars always have ridiculous wings because usually when they're climbing up mountains like Pikes Peak, the air gets thinner as you go higher up, so you need more things to generate downforce since your density decreases. So that's why they're always very large, massive wings. So how does a wing work? It basically works completely opposite of an airplane wing, where in an airplane you're trying to fly, and it makes for a really bad day if you fly in a race car. So we don't want that. So we basically flip the wing upside down to force the car into the ground. And so you can see the high pressure zone on top of the wing is going to push down on it, which will subsequently push the wheels down into the ground and create more traction, which is what we want. And similar to that, you have to balance your downforce forces. So if you have all of your downforce in the rear, you're not going to have very much front grip. So if you try to take a high-speed corner, you're just going to turn the wheels and go straight into a wall, which is, of course, bad. And likewise, if you have all of your downforce on the front, if you try to power out of a corner, you're just going to spin. So you have to balance the forces, and that's mostly what we've done here. And this is our final results of the drag model. So you can see we increased our overall drag coefficient by 0.09, which is kind of to be expected because anytime you're adding downforce, you are unfortunately adding drag. And our lift coefficient decreased a pretty good bit, which means we're making more downforce for going through the same speed of air. And these are our actual values. So you can see we chose to iterate this in steps of 10 meters per second from 30 miles an hour to 125 miles an hour was what it converts out to, just because it's easier for most people to understand those speeds. We chose those speeds because that's most likely the range where the car is going to be operating. If you're going below 30 miles an hour on a racetrack, you are definitely not winning. And most tracks, for at least the power limitations that the car has due to racing in its class, it's just not going to get over 125 miles an hour. So we chose to emphasize this area. If you go to the next one. So that was our downforce. So this is our drag force, which obviously increases with speed as well. And again, we chose to analyze from 30 to 125 miles an hour because that's the zone that we really care about. And so our final results were at 125 miles an hour, we generated 1,700 newtons of downforce. And that represents a 260% increase over the stock body of the model. And then at 60 miles an hour, we generated 200% over the stock body. And of course, as you go faster, you're going to generate more downforce and subsequently more drag because, again, it works inversely to an airplane, whereas you go fast in an airplane, you create more lift, which, again, is bad. And then for our drag force, we generated 1,500 newtons at 125 miles an hour, and this is a 150% increase over the stock body, which, of course, is bad. So if we were to go to the next slide and talk about our improvements. So we want to really optimize drag and downforce, because again, as you create downforce, you create drag, and you want to you only need as much downforce as the car requires, because if you're creating unnecessary downforce, you're going to blow through tires faster, and of course you're creating more drag, so you're going to go slower. So ideally, we would calculate exactly how much downforce we need for that car on that track in these weather conditions, but unfortunately we just don't really have the capacity to do that. So we would come into our next design revision that we would make, which is a variable AOA wing, which stands for angle of attack. And so that is the actual angle of the wing. Of course, as it's more down, it's going to create more downforce, and more flat, it's going to start to create lift like an airplane. So we would, on different tracks, will require different levels of downforce. So if you're on a pretty straight, high-speed track, you don't need that much downforce. Whereas if you're on a very intricate, medium-speed track where you're taking high-speed corners, you definitely want a little bit more downforce. So that's something that we would be able to change track to track on the fly, but it's just so hard to model without doing a little bit of trial and error. And then, of course, if we could get access to the full ANSYS software, we could do a lot more things like calculating the rotation of the wheels, using a better model, because we're limited just by how many elements we can do in the student software. And that is all. Does anyone have any questions?
Question.
Colin.
Actually, I have one suggestion.
Okay.
When you showed the improvement from the old base data to the new data, the graph, you change your bounds. So the graphs are identical, right? It's just kind of hard to read, and I feel like I couldn't see your magnitude of improvement. I did it in your numbers, which was awesome. It's pretty cool to see like the steeper graph versus the
Okay.
graph. But
Okay.